Hello everybody, my name is Rudra Pratap Singh and today I present you my design of my rocket Varuna. Varuna is modeled to execute my target to carry a wide range of missions while carrying a versatile payload to a height of approximately 1420 meters in a quick burst of high speed while maintaining in-flight stability and in a small structural frame. Now I will go over the blueprint. Dhruv is Varuna is a high-powered single-stage dual-cluster rocket powered by two G55W rocket motors. It stands at a height of 25 inches and weighs 754 grams. The, seven, the center of gravity is present located at 13.961 inches and the center of pressure is located at 17.722 inches. The launch stability clocks in at 1.5 cals. Now I'll go over fixed components. The cone. The cone. The cone is a 6-inch long and has a diameter 2.5 inches. It is polished PVC of hacked series of cones. These parameters were chosen to optimize the core aspects like stability and drag reduction, while having enough internal capacity to hold a PVC inner tube of 4.5 inch in length and 1.1 inch in diameter. This inner tube is the payload holder. The cone is from Hack series as they provide the most drag reduction among all other shapes and allows the rocket to reach the desired height more easily. This shape also gives us the desired dimensions for the inner tube. The shoulder of the cone is 1.6 inches long and 2.2 inch in diameter and 0.5 in thickness to ensure structural security and provide enough stability to the model. The payload is a versatile piece of equipment here. The payload is placed in an inner tube presented in the cone, and the rocket has a capacity to lift a 4-inch long and 1-inch wide payload of 50 grams to 300 grams while maintaining in-flight stability. These dimensions were once again chosen to expand the options of mission the Varuna can run. These dimensions allows Varuna to pick up from altimeters to calculators to thermometer, barometers, and other means of scientific experiments any person would like to conduct. This payload also helps in maintaining stability by adding excessive weight on the cone. Now I'll go over the body. The body is 16.934 inches long, 2.5 inch in diameter, and is polished PVC body and houses enough space for all components. The parachute. The parachute is a ripstop nylon canopy of 47 inches with 6 shroud lines of 11 inches. This ensures the safest descent speed possible for the rocket after reaching apogee. The launch lug. The launch lug is made of 1-inch long PVC and is placed directly outside center of gravity to ensure launch stability. This placement of launch lug also enables the rocket to avoid misfire and changing of direction on the launch. And this ensures the rocket only moves vertically and stably and possess enough stability during launch. Now I will discuss the motor. The motor is comprised of two G55W motors forming a dual cluster mount fixed in an engine mount of the body which possesses a length of 7 inches and 1.02 as diameter. Finally, the two engines are said to have an overhang of 0.5 inches to ensure proper thrust, stability, and without compromising structural strength during flight and landing. Then the whole motor section is then secured by two centering rings, centering ring A, centering ring B, to increase structural strength. And then finally, a steel bulkhead is added to keep the foundation strong and secure the base and stop the rocket engine from moving forward. These bulkhead, both the centering ring and the bulkhead, is made of steel to add weight to the rocket, which was needed to bring the stability to a desirable range and get the CG at the right position. The rocket possesses three troposodial fins with root chord 1 inches, tip chord 1 inches, height 3.181 inches, sweep length to 2.576 inches, and sweep angle of 39 degrees. It is made of polished PVC and airfoil and has airfoil fin cross section. This type of long fin shape is a main enhancing feature of this design, which allows it to achieve the stability it needs and the height it needs to achieve. This is able to happen because the fins are able to concentrate the opposing wind out behind the engine, ensuring proper acceleration and increasing the lift capacity of the rocket. This thus increasing efficiency of thrust. This shape was chosen after much deliberation and much experimentation, much experimentation and watching many stimulation over results of different fin types. And finally, the best one was chosen. This, combined with the short but thick nature of the model, allows near cancellation of unwanted rotation, which may hamper the vertical flight of this rocket. Now I will go over the reason for the location of center of gravity. The center of gravity is located at 13.961 inches, about 4 inches directly above center of pressure. This was done to ensure proper lift and flight stability. As the CG is near the center of rocket, the CP is able to easily lift the whole mass of the model without much inefficiency. And with the CG at the center of the rocket, we are also able to negate the gradual movement of CG as the fuel runs out and the rocket loses mass during the flight, thus ensuring flight stability. Stability margin. Dhruv clocks in at a 1.5 with payload of 30 grams during launch time and maintains a stability range of 1.60 to 2.4 throughout the flight. And this rocket and this was done by using counterweight like the bulkhead, steel bulkhead, and the steel counter centering wings, and by increasing thickness of the cone and body from different proportions to increase stability and bringing the CG at the right positions. Technical challenges. The model presented a high difficulty in choosing proper dimension for the fins. This problem nearly made me scrap my idea as I was unable to stabilize the high power output of the cluster modules. But this was overcome by running numerous stimulation and calculation over a wide range of sample space of different dimension and options. Then in using integration to find the integration and mathematical means to find a sweet spot for my fins. And this allowed me to choose the best possible dimension and the shape. The other technical challenge encountered was that the parachute was unable to deploy properly because of the high speed presented by the model. This was then solved by an unconventional means, which is to deploy a large parachute after 3 seconds of descent, giving the safest range of operation for the parachute, thus achieving a decent grounding velocity. Now I'll go the various graphs related to the model flight. This is the first default stimulation one of the model, where we can see the model velocity of the rod during the launch is 20.9 meter per second. Apogee reached is 1417 meters. Optimum delay is 12.5 seconds. Max velocity achieved is 260 meter per second. Max acceleration is 215 meter per second square. Time to apogee is 15 seconds. Flight time clocks in at 576 seconds and ground velocity is a small 2.65 meter per second. Now the stability time graph. As you can see, with a payload 30 grams, the rocket shows outstanding stability management by staying in the range of 1.2 to 2.4 during the most extreme casing and then dropping to constant and experiencing constant drop to velocity and staying in the range of 1.5 1.3 after deployment of ejection deployment of recovery device. flight side profile. This is a launch. Burnout time. Burnout time. The pad deployment of parachute. Grounding. As you can see, as you can observe in this graph, you can see near cancellation of unwanted rotation which may hamper the flight. Now I will go over various ranges of payload this may carry. When we increase the payload to 150 grams up from 50 grams, you can see it can still reaching 1398 meters and clocking at a stability of 1.99 cals. And the ground head velocity is still a sweet spot of 2.9 meter per second. Stability versus time. The stability time is still in the healthy range of 2.1 to 2.8 and dropping from 2.8 to 2.4 after deployment of recovery modules. Now increasing the payload weight to 270 grams. As you can see, the rocket still is able to reach 1336 meter and clock at a stability of 2.45 cals. The ground head velocity this time is 2.66 meter per second. The rocket is still able to stay in a healthy range of 2.4 to 3.1 and then dropping from 3.1 to 2.8 after deployment of recovery modules. Now increasing the weight from 270 grams to 300 grams. Now the rocket is still in the healthy range of 2.5 to 3.2, then dropping from 3.2 to 3 after deployment of recovery module. Now I will go over various perks of this model, Varuna. Varuna is a versatile design of a rocket which has emphasis on high speed, high stability, and reusability and versatility. The Varuna is able to carry a wide range of missions very easily and able to reach the apogee very quickly and efficiently